It's my pleasure to be here. I'm Jess Gehin. I currently work in our nuclear technology programs office as a senior program manager, but before that, for 5 years, I ran our reactor analysis group. And my background is reactor physics and neutronics. I've worked at Oak Ridge for about 20 years now, working in the area of reactor analysis and reactor physics. Thank you. These types of concepts are something that let me dump this. Is that okay?
Yep.
All right. So I'm very interested in this. This is something I follow very closely. I'm going to give a talk of some of what the interest and directions for molten salts, and there have been some changes in this as far as DOE programs that I'm going to talk about. And I'm also going to hit some of the things that have already been talked about, so I won't spend much time on that. Okay. So the main point of this slide is if you actually follow Kurt's blog and other things, you might be convinced Oak Ridge is actually in black and white. But that's not true. We actually have color at Oak Ridge, and we've over the last 10 years have actually there's been a lot of investment in Oak Ridge and sort of revitalization. We've got a large budget. We're actually the largest office of science laboratory that DOE has. And a lot of that is focused on energy, not just nuclear, but a wide range of energy. We've got 4,500 employees, a lot of guests for our research facilities. You can see we've spent about $500 million in new buildings. This, for example, is one of our new buildings. World's fastest computer, something that can be applied to reactors, and that's something that we're definitely working on. We've actually submitted a proposal for this modeling simulation hub, which I can't say a whole lot about because we're in the middle of a competition for that, but that's something we're working on. We have our accelerator source and our reactor source, so neutron sciences is an important research area for us. Anyway, we're a big laboratory. We like solving complex problems, and we always have. So we go back to what most people see of Oak Ridge. This was our initial heritage, the graphite reactor. And if you actually go back and look at the description of why Oak Ridge was founded, there were actually 4 original missions. And you're familiar with the first 3 of these related to materials for the Manhattan Project. But the last one, fission reactor separations, research and development, is probably something that most folks didn't realize was part of our original mission that they thought about when they first founded the lab. The technologies would be useful for civilian power as well. And we've exploited that over the years and continue to today. Okay, recently there was a nice report that Murray Rosenthal put out on the 13 reactors at Oak Ridge. I put pictures of most of them. You'll count, there's only 12 here, but actually this tower shielding reactor, is there a pointer? Okay. Anyway, I'll just use this one. So there's actually 2 tower shielding reactors. We built a number of very interesting designs. 4 of these are relevant to fluid-fueled reactors, which they call homogeneous reactors. These top 4 in the middle, ranging from homogeneous reactor experiment. These were aqueous reactors, and then the salt reactors that everybody's familiar with. The one reactor that still operates is the high-flux isotope reactor, which is now about 40 years old, but still going very strong. So I'm not going to actually talk about the MSRE and molten salt reactors. That's been covered pretty well. But what I am going to talk about, and I think David referred to some of this, is there was an interesting time in the late 1970s. If you remember, in the mid-1970s was when a lot of the concerns over proliferation rose, and you might think that was actually a bad time for reactor technology development. You'd think it'd be going down, but those folks that were engaged in nuclear technology development, reactor development, were very creative people, and so they wanted to see their technologies continue, and worked on several concepts that address proliferation. These don't get mentioned very often, but they're very relevant today, which I'll talk about in a little bit. But these include you've got a break-even molten salt breeder reactor. I'll call it breeder reactor to try to address some of the proliferation issues that they were concerned about at the time. They started looking at systems with simpler processing. So you've got a system without fluorinators. I know people will cringe. Some of you in the room will probably cringe because the fluorination process is one of the key reasons they started developing this technology. But that means you basically have no separated U-233. Systems with only rare earth removal and a thermal reactor. The rare earths are the primary fission products that are absorbing neutrons. So they simplify the processing to a batch type system with no on-site processing. We've already mentioned the natured molten salt reactor. So these interesting concepts still are evolving, and it's more than just what you traditionally think of the molten salt reactor. So you can add another concept. I won't go into this in a lot of detail. I pulled out a historical slide that we used to use a lot. Oak Ridge worked with Sandia and with Pear to develop this concept about in the 2000 time frame, I think, when it first evolved. And it combines, as we all know now, a lot of the technologies from both gas-cooled reactors, but in molten salt reactors as well. And so we've been working on that since that time. Activity's been up and down, but it's on an uptrend right now, which is very exciting for us. So we worked primarily from 2000 to 2006 on a fixed geometry, prismatic derivative type geometry, whereas Berkeley continues to develop the pebble bed, which you just heard a couple good papers on. So in the last 2 years, most of the effort at Oak Ridge has been on technology development and technology evaluations, including component testing, material development. So Pear mentioned the long lead time for material. Well, it turns out Hastelloy-N is not in the section 3 of the code. I think you mentioned that, which is a concern. So we have to look at different materials, perhaps materials that are in the section 3 of the ASME code, but perhaps coated with nickel or other things. And then also liquid salt heat transport. The high heat capacity means liquid salt is good for lots of applications involving heat transport. And so we continue to look at technology developments. We're not actively working on a reactor design, but we're looking at a lot of the supporting technologies. And included that, we're developing a 1/4 megawatt salt loop that we can use to test fuel. There's a cartoon here, but basically the interesting thing about this in this test section right here is that you can inductively heat material. So the idea was, particularly for the pebble bed, you can put pebble geometries in there and heat them with inductive heating to get something that's typical of the conditions you might see in a reactor, where the heat actually evolves from the pebble rather than the coolant inwards. So that's one thing that we're excited about. And we're using internal resources to develop that. So one thing I wanted to emphasize, and Pear said this as well, we see the path to the molten salt reactor development is through the fluoride salt-cooled reactor. Pear said this well. So the salt-cooled reactors now rely a lot on the developments of the 50s through 70s at the time, but the technologies that we're working on now are going to be fully applicable to future molten salt reactors. So the two futures are linked. One reason why the salt-cooled reactor is something you should all be interested in seeing develop, because the materials and heat exchangers and all the components that have been developed can be applied to the molten salt reactor. Let's see. And so it means we can leverage the investments, which is interesting. If you look at the current high temperature systems, which are gas cooled systems, compared to the fuel cycle systems that were looked at, which are sodium cooled systems, there's very little commonality in those systems. And these systems, which go after high temperature and also fuel cycle, there's strong overlap. So that's one thing. We are planning a workshop on the salt cooled high temperature reactors.
We've heard several talks now, and none of them refer to the price of electricity from these new systems. And it seems like that's a very important issue, because GNEP basically crashed. This was DOE's program. It crashed over the fact that once through was going to be the nation's approach because of cost. And so when you speak of these different systems, and nobody mentioned cost, including the DOE itself doesn't put cost among the 5 components up there. Well, then it looks like it's kind of a fake program. Well, if cost isn't the dominant thing in nuclear, and if it doesn't drive the cost of electricity down, it's not going to have a place.
Okay. Yeah, that is true, and you know, commercially, it's very hard to adopt things that economically don't make sense, so that doesn't happen. We keep relearning that lesson, I guess, but I'll point out a couple things. First of all, you know, if you look at this second bullet here, and this is directly from DOE, affordability is important, and so that's something that they recognize as having to develop now. When you look at other systems for fuel cycle, there are other economics apply. For example, the cost of disposal. Can you do that economically? We are looking at the cost of, as part of this study I mentioned, of molten salt reactors, at least this top-down approach. For those of you familiar, back in the 70s when they did their economic studies, the molten salt reactor was on par with the LWR. So we've escalated all those costs, and while it's difficult to come up with capital costs from top down rather than bottom up, we see no reason why they shouldn't at least be on par with light water reactors, including the fuel processing system in this case.
All right. You want to take one more question? All right, let's do it. There you go, Lars. Hey, Lars.
I was just going to clarify further with that. If you listen to Dr. Peterson's talk, the reactor size, the whole containment vessel is a half and sometimes down to a quarter of the size of an LWR. We aren't far enough in the designs to be able to translate that into dollars, but just intuitively, if you've seen those big structures, you're going to make them and all the pumps and everything else inside of them dramatically smaller. It's going to come back to the cost line at the end.
Yeah, there's going to be a whole presentation about cost at the end of the day. So thank you very much.